Hello. So this is module number 12 on mathematics and astronomy, and I've divided it into 3 parts. So there are 3 parts to watch, and it's just kind of too long to watch all at the same time. So just to kind of give you a heads up, you've got several things to watch on this one. So let's get started. First of all, this is one of my favorites because of the blend of math and science here. This was a time where science and math are both growing at the same time, and the work in one is truly affecting the work in the other. So advancements in mathematics are pushing advances in astronomy. At the same time, advances in astronomy are pushing advances in math. And it's just really neat to see that. And when we talk about Galileo, you'll see some of the things that he did. And I'll remind you a little bit about what's going on with calculus and some of the things that you did in calculus. All right, so let's look at the PowerPoint, the first PowerPoint. This is Math and Astronomy Part 1. And come on. Charlie heard somebody across the street. All right, so Math and Astronomy Part 1. And there are several people to talk about in this module, and it starts all the way back with the ancient Greeks. So Claudius Ptolemaeus is one of the ancient Greek mathematicians and scientists. And I've got the 2 pictures of him here because, sometimes people get him mixed up with the Ptolemies, who were the pharaohs in Egypt. So the picture on the right shows him with a crown on his head. Well, he was not royalty. He was a Roman citizen of Greek ethnicity. And on the left, you see him, and he's got that tool in his hand. He's pointing to the sky. That's Ptolemy the astronomer and scientist. And you don't pronounce the P, it is Ptolemy or Ptolemaeus if you pronounce it in the Roman way. He was a Roman citizen, probably Greek. We call him Ptolemy. Not only was he a mathematician and astronomer, he was also a geographer, astrologer, a poet. We have seen so many of the mathematicians who have had several hats, who have been involved in several different academic areas. Well, like so many of those other Greek mathematicians, he lived in Egypt, lived and died in Alexandria. His work was written in ancient Greek, but we have it today thanks to the Babylonian, thanks to the Islamic translation movement. He used the Babylonian astronomical data. That's where the Babylonians came in. So the data that he used to come up with his ideas were from the ancient Babylonians and what they observed was happening in the sky, how they saw things were moving, how long it took them to move from here to here, where everything was with respect to everything else. He took all of that data, analyzed it, and published it in this book called Almagest. Almagest is a book for your list. This is one of the famous books. It's really important. The Greek title means the mathematical compilation. Later on, it became the greatest compilation, hence the EST. In Arabic, and that's where we get the title today from the Arabic translation of the Greek title, means Almagesti. So Almagest, that we're calling it today, comes from the Arabic title Almagesti. It contains his theory of how the sun, the moon, and the planets all moved around relative to each other. And this was the prevalent theory for 1400, 1500 years. So this lasted a really long time. Within this book, and here's a good example of math and astronomy building on each other and affecting each other, he's got trigonometry. So he's got the beginnings of trigonometry here, looking at chord functions in intervals of 1/2 degree. So the idea here is that you've got a circle and you've got these central angles that are measured in 1/2 degrees, 1/2 degree, 1 degree, 1.5 degree. What's the length of the chord that's cut off by that angle? So that's what the chord function is, the length of the chord that's cut off by that central angle in a circle. Also in this book, he's got formulas, and they're accurate for finding the sine of the sum and difference of 2 angles and the sine of half angles. So the other trig functions come later. The sine function was the first one that was actually used. His approximation for pi was 3 and 17/120, which is very, very close to what it is. which rounds off to about 3.1416. Okay. All right, now here's what his model of the solar system looked like at the time. Ptolemy put the Earth at the very center. And he's got the center of this sphere-like solar system. So the universe, and no, I shouldn't, but I'm using those terms interchangeably. The universe is a sphere, and the outer sphere is where the stars reside. So you see that outer sphere, and it's got stars on it. That's where the stars are. At the very center of that circular sphere is the Earth, which is a circular sphere itself. And then outside that Earth is another sphere, a shell, and that's where the moon is rotating around the Earth in a circular orbit, but the Earth is at the center. And then outside of that is Venus. It's going around the Earth and the moon in a circular orbit. Outside of that is the sun, and it's got its own shell, which is traveling in a circular orbit. And then you've got Mars. Now, at the time of Ptolemy, Venus and Mars were the planets that he could observe. And he believed that the sun was between Venus and Mars. Everything was circular back then, or he believed that everything was circular in terms of the orbits. And you've got these shells inside shells with the Earth at the very center. Okay, so the Earth is in the center, everything's circular, moon goes around first, then Venus, then sun, then Mars. Then you've got all the stars coming. Well, after Ptolemy really dug into his data and he started looking at what the numbers told him about how these heavenly bodies actually moved, he said, you know, that's close, but not quite. And he had to make two adjustments. Okay, so do you see that circle, big circle in the middle, and there's the little dot in the middle that says center. All right, he said, well, you know, the Earth isn't exactly in the center of that orbit. It's just a little bit off. So the Earth is at what's called an eccentric point. On the opposite side of the center, the same distance from the center to the Earth, is a second point called the equant. And that point, notice, is connected to that circle up there that's going around the circle. You've got the Earth in the center, not smack dab in the center, but it's in the center of that circle. And then the moon is going around the Earth, but it's not going around in that circular orbit. It's going in a circle that goes around the circle. So it goes like this around that circular orbit. It's circling around the circumference of the circle. Okay. And that circle, this one that it's circling around, is not centered, isn't connected to the center of the big circle. It's connected to that equant. So that's what's controlling that circle that the moon is moving around. And then that circle is moving around the circle that the Earth is in the middle of. Okay. So there are several models that you can look at. YouTube has several models you can look at. I'll post a couple of, or post at least one of those on our Canvas site so that you can look at how this works. Okay. But Ptolemy made those two adjustments. So he recognized his data was insufficient, or his model, let me put it this way. The data was how things really are. His model was insufficient to explain the data. He made these two adjustments, and wow, it's amazing how close this was to what he could observe. Okay, now remember, this is way before we've got really advanced telescopes and all kinds of things to help us out with what's going on up there. Okay. But 1400 years later, along comes a Polish astronomer and mathematician named Nikolai Copernicus. And Copernicus is the person who's going to blow this out of the water. He said, no, it's not what Ptolemy's telling us about. It's not a geocentric model. Geocentric puts the Earth at the center. Geo is from the Greek word for Earth. Think geometry, geology, geography, geocentric. And Copernicus said the sun is at the center. So it's not us at the center of the universe. It's the sun at the center of the universe. And the earth is just one more planet going around it, like all the other planets. So Copernicus lived in Poland, up here in Northern Europe, and this was going to cause quite a stir in Southern Europe within the Roman Catholic, within the Holy Roman Empire, the Roman Catholic Church that has built a foundation of faith on the Bible and what the Bible says is absolute truth. And you aren't supposed to come up with any contradictions. You're supposed to take it exactly like we explain it. No interpretations. This is the way it should be. And they've always said the earth is at the center. God controls it. God made us. He put us right in the center. So the Pope and the people in Rome are not going to be very happy about Copernicus and his views. Although, let me mention right here, Copernicus was a devout Catholic, and he was very concerned about the problems this might cause his own faith, his own church. And so he showed it to the Pope at the time, the Pope that was alive when he wrote the book, and actually dedicated his book to the Pope. And the Pope, which is kind of interesting, the Pope knew what was going on, didn't seem to have a problem with it. No big deal as far as Copernicus was going on. Okay. Then after Copernicus, there's another mathematician and scientist who's living in Northern Europe. This is Denmark. So this is the part of Europe that's kind of far away from what's going on down here in Rome. And we're up here in Northern Europe where the Protestant Reformation is going on. So there's a lot of societal upheaval right now, a lot of things happening in the world. Tycho Brahe is an astronomer, and throughout his lifetime, he collected data over what was going on in the heavens. So for 38 years, from various places in Northern Europe, he built observatories and he collected this data and recorded it. He didn't do anything with it, but he recorded this data about what he could see and how things were moving and how they were related to each other. Before he could do anything with it, he died. And I'm going to move on to the next one real quick. I'll come back to this. Oh, no, actually, let me tell you where we're going from here, and then I'll talk about here. Before he could do anything with it, he died, and he passed this data along to his student, whose name is Johann Kepler. Kepler's who we're going to talk about in the next video. All right, let me pause. All right, so let me go back to the slide that we were on. Tycho Brahe collected all of this data, and it was given to his student when he died. Now, in the meantime, here's where I'm talking about the connection between math and science. In the meantime, there's this mathematician in Scotland who is an amateur mathematician. He's a Scottish nobleman, so he's got lots of land. He's very wealthy, so he does this for fun, but he's very interested in computation. He likes working with numbers, and he likes combining numbers and see what happens. So one of the things that he does is he publishes this little book called Rhabdologia, in which he explained what are called Napier's rods or Napier's bones. And this is what they look like. So if you had a set of Napier's bones, you would have a set of these, and you would have 10 of them, at least 10, one with a 0 at the top, 1, 2, 3, 4, 5, 6, 7, 8, 9. And down the rod, you can see there what you have. Look at the second one, the one that has 5 at the top. This is your fives table. So the first column the first row under there is 5 times 1, then 2 times 5, 3 times 5, 4 times 5, 5 times 5, and so on and so on. And what he did with these rods was combine them to do multiplication and division. So the rods already have the multiplication facts on them, and you can very quickly do long multiplication, a 3-digit number by a 3-digit number, by using these rods without having to remember your facts. And you just choose the appropriate rods, put them down side by side. Now you do have to add. So you have to add the numbers together, but you can very quickly do computations. And this turned out to be wildly popular with his friends and neighbors. And when he would have parties, people would ask him to pull these out and demonstrate how this was used. Kind of interesting. But in the history of math books, he's really known for his logarithms. So he really took this computation stuff seriously. And in 1614, published another book in which he's got these tables of logarithms. So tables of numbers after numbers after numbers. And this was why he did it. Seeing there is nothing that is so troublesome to mathematical practice, nor that doth more molest and hinder calculators, he means people who calculate, than the multiplications, divisions, square, and cubical extractions of great numbers, which besides the tedious expense of time, are for the most part subject to many slippery errors. I began therefore to consider in my mind by what certain and ready art I might remove those hindrances. So he figured out with those rods, he could pretty easily do multiplication. Division was a little bit more complicated with it, but really easy to do multiplication. But division, square roots, cube roots, how's he going to do that? Not with the rods. He's using these tables. And he defined a logarithm. Okay, very, very different from the way we define a logarithm. All right, consider two lines. You've got line AB, which is actually a line segment. It's got a fixed length. And you've got AX, A prime X, which is actually a ray, infinite in length in one direction. And on each of these, you've got a point C on AB, you've got a point C prime on the ray, and they start over here on the far left. They start over here at A and A prime, and they're moving to the right. Okay. When they start moving at the same velocity. So C moves away from A, C prime moves away from A prime at the same velocity. But think about it for a second. That bottom ray is infinite in length. So if C prime is moving along that ray, no big deal. It's going to just keep going and going and going. It's moving at the same velocity, just keeps moving. Well, up there on that line segment, if C is moving at that same velocity, at some point it's going to hit B and stop. If the velocity doesn't change, if it doesn't slow down, it is going to end up using up all the space and run into B and stop. So he recognized that he had to do something different. All right, so C prime is moving along. Its velocity stays the same the whole time, but C starts off at that same velocity, but it starts immediately to slow down. And its velocity is proportional to the distance between it and that endpoint B. So look, as C moves to the right, the distance between B and C is getting smaller. And as C moves to the right, then its velocity is going to decrease. All right, so there's the physics of it. That's what's going on. And so Napier said on the ray at the bottom, A prime C prime is Y, and BC, the distance between the endpoint and C, is X. Y is the Napier logarithm of X. All right, so as C and C prime are moving along, Y is growing at a constant rate. X is getting smaller and smaller. Okay. All right, so that's what's going on here. Well, another mathematician in England came across this and said, this is genius. Imagine we've got these tables now that will allow us to do all of these computations easily, quickly, without all of the fuss and bother of the time involved, of the possibility of making mistakes. But dang, that's kind of hard to understand. His name was Henry Briggs. Henry Briggs comes along in 1615 and he recognizes how brilliant this is. He travels to Scotland to work with Napier, and he says, I have an idea. I think we can make this better. His idea is to change it so that 10 is the base of the logarithm, and that the log of 1 is going to be 0. the way we understand base logarithms today. Log base 10 of a is equal to b, because when 10 to the b power equals a, and think about it, log of 1 equals 0 because 10 to the 0 power is equal to 1. So Briggs went back and worked with Napier on this. Briggs, pretty much all by himself, recalculated all of these tables, came up with brand new tables of numbers based on this new definition. Those tables are the ones that 60 years ago, 50 years ago, were in the back of algebra books, calculus books. Now we don't need them. We use our calculators. But these logarithms that Napier and Briggs invented provided Kepler with the background that he needed to help him figure out the mystery of the data that Brahe had left him. So that's where we're going to start in part 2 of mathematics and astronomy. Okay, see you there.